Hello, everyone. You're all doing well. So hopefully you have turned in your first lab online that was due on Sunday. If you had any issues with that, go ahead and hang around after class and we can talk about it. Otherwise, we also had a mastering chemistry homework assignment due, and that's just sort of how the weeks are going to go from here on out. Is you're going to have a quiz, a lab due, a mastering chemistry, quiz, lab, mastering chemistry, and then we have tests sprinkled in there. So your first test will be not this upcoming Sunday, Monday, but the following Sunday, Monday. Okay, so just keep that in your mind's eye that we'll be having a test coming up here soon. Okay, so we left off talking about matter and energy. We got all the way through all the matter stuff. This different states, how we define matter as being either an element, compound, homogeneous, or heterogeneous. We went over physical properties and chemical properties, phase changes, went over the basic structure of a chemical reaction. So we have reactants, right? We went through all this. Did we left off at temperature, I believe. That was the note that I put on my thing. Talked about distillation, conservation of mass. Conservation of energy, calories, joules. We did this. Is that where we left off, the calorie conversion? Sorry, I'm trying to remember. You can throw it in the notes or the chat. I thought we had talked about that. We left off sort of around here, around exothermic. Slide 52. Okay. Yep, right around there. Okay. So we had discussed converting between, nutritional calories and joules. Always make sure that you're, are you talking about big C calorie or little c calories? Big C calorie, which is our nutritional calorie. There are 1,000 little c calories in one of those big C calories. And then the relationship between joules is with little c calorie, not nutritional calorie. So you do have to do 2 hops if you are going from big c calorie into joules. So energy is constantly shifting states in the universe. Here we have a weight that was brought up to the top of this building, and then at the very top here, it has a high quantity of potential energy because you used kinetic energy from your body to move that weight up to the top. It's kind of got more of an effect from gravity than the weight down at the bottom. So if this thing was to fall, it's unstable or it has a high potential energy, it wants to move towards a lower potential energy. The way that that would happen was this weight would fall. The potential energy in it would turn to kinetic energy. It would hit the ground, and when it hit the ground, that kinetic energy would shift into heat or thermal energy. So there's other things that have high potential energy. Substances like TNT have a certain configuration of their molecules where they want to undergo a rapid chemical change. And in that rapid chemical change, there's an explosion. So certain things are more unstable than other things. You have something like water, H2O, that is a relatively stable molecule. It doesn't, want to decay, and when it does break apart, it doesn't release like a whole lot of energy or anything like that. So in a chemical reaction, you can either have an exothermic reaction or an endothermic reaction. In an exothermic reaction, that's this top one here, we've got energy on our y-axis. Energy is higher as you move up. The reactants have a higher energy than the products, okay? So your reactants have a bunch of like oomph to them, a bunch of potential energy, and that potential energy is released during the chemical reaction, and then you end up with these products that are like more stable and kind of puny, okay? They don't have as much energy packed in them. If everything was an exothermic reaction, if everything was high energy in the beginning and it released energy to become low energy, then nothing would have energy in it, right? So there has to be an equal and opposite thing to this exothermic reaction, and what that is in an endothermic reaction. And that's where you have reactants that are low energy, but when they come together, they absorb, they suck energy up from the surrounding environment to create these products that have a lot of energy or a lot of stored potential energy. So we have both of these happening simultaneously. Usually in an exothermic reaction, that energy is being released. So you'll see like a loss in heat or a negative value for heat values. In an endothermic reaction, you're absorbing the heat, you're absorbing the energy, so you have a positive value. And we'll look more at that quantitative number. So when talking about heat and temperature and specific heat, there's all these different words for different things. So we want to make sure that we keep these straight. Temperature, when we measure temperature, like the temperature of the air, that is a measurement of the material's thermal energy. How much thermal energy does it have? And what is thermal energy? Thermal energy is the random constant motion of particles. So all matter, even if it's a solid, even if it's a really, really cold solid, there's going to be this motion to the particles. The motion gets bigger, the vibration gets bigger as you move through solid, liquid to gas. How do you go from a solid to a liquid or a liquid to a gas? You add heat. The heat increases the thermal energy, which then will in turn increase the temperature. So when you're measuring the temperature of the air outside at like 85 degrees Fahrenheit, you're actually measuring like the air's molecules hitting that thermometer. So the hotter an object is, the greater this random motion is, the higher the temperature will be. That's different than this word heat. Like sometimes when we think of the word heat, we think, oh, that means temperature, but that's not actually the case. Temperature is going to be, the values we have for temperature are things like degrees Celsius, Fahrenheit, Kelvin, okay? Heat is a unit of energy, and it's really talking about the transfer of energy from, or the transfer of thermal energy from one object to another, or the shift in energy because of a temperature difference. So like taking an ice cube and sticking it in warm water, and the ice cube starts to melt. Why? Because there's a heat transfer from the hot, warm water to the cold, the ice cube, and it allows it to melt. So this is a value of energy, like how much heat did that warm water give? Okay. It's a quantitative value. You can actually calculate it in joules or calories or whatever. Temperature, by contrast, is a measurement of the thermal energy of the matter, not the exchange of that thermal energy. So temperature is more of like a fixed value. It's like this thing has this temperature. Now, heat is dependent on temperature, but temperature is for a fixed object. Heat, on the other hand, is saying, hey, this object is then transferring its heat to another object. So, you know, the pot of boiling water, the temperature is 100 degrees Celsius. You stick your hand in it, and now your hand is burned because heat transferred from the boiling water to your hand. Don't put your hand in boiling water. Yeah. All right, here are the units for temperature. So Fahrenheit is probably what you're most comfortable with, but it's also the least practical to use. 0 degrees Fahrenheit is the freezing point of a concentrated saltwater solution that has a very specific concentration. It's like, well, why did they use that? Why didn't they just use water? Body temperature, 96 degrees Fahrenheit. The important things that you want to know: water freezes at 32 degrees Fahrenheit and water boils at 212 degrees Fahrenheit. Again, totally random numbers, right? They don't like really correlate with anything even. Room temperature is 72 degrees Fahrenheit. Now, if we move over to the Celsius scale, water freezes at 0 degrees Celsius. Isn't that nice? And water boils at 100 degrees Celsius. Clean, nifty, easy. Room temperature is approximately 22 degrees Celsius. So 22 degrees Celsius may sound cold to you, but that's actually, you know, it's in the 70s. Kelvin is a scale that is directly related to Celsius, and that you're just taking whatever your Celsius value is and you add 273. So you shift the whole scale over by 273. Why do you do that? Well, the Kelvin scale avoids negative temperatures. So it assigns the lowest possible temperature as 0 degrees Kelvin, and then everything goes up from there. 0 degrees Kelvin is known as absolute zero. Why do we want to get rid of negative values with temperature? Sometimes when we're running calculations, we don't want a negative number for our temperature, because what is temperature measuring? It's measuring the thermal energy, right? It's measuring the vibration of the particles. How can you have negative vibration, right? You could approach zero vibration. Those particles could slow down so much they almost get to zero, but you can't like inverse or negative the charge or whatever on that. So Kelvin just gets rid of that whole thing for us. So on Kelvin scale, water freezes at 273 and water boils at 373. 100-degree difference between freezing and boiling, 100-degree difference between freezing and boiling. Same magnitude because it's just shifted over. So 100 degrees Celsius and 100 degrees Kelvin separate our freezing and boiling of water. 180 degrees separates it on the Fahrenheit scale. So there's a calculation to convert between Celsius and Fahrenheit. This is one of them. This one, the top one is for Kelvin and Celsius, or Celsius and Kelvin. So if you want to get Kelvin from Celsius, all you do is add 273, or in this case, they did 273.15. It's a little bit more complicated for Celsius. If we want to get Celsius from Fahrenheit, we need to subtract 32, and then we need to divide by 1.8. Now, let's say instead of solving for Celsius, we want to solve for Fahrenheit. Well, degrees Fahrenheit is going to equal our Celsius value times 1.8 plus 32, right? So if I isolate the variable 1.8, multiply this by 1.8, and then we'll add 32 and add 32. So that's where I'm getting that value from. So Fahrenheit is Celsius times 1.8 plus 32. This isn't anything challenging, but I want you to do one problem with those equations. So what is the temp in Celsius and Kelvin for a room at, let's say it's 84 degrees Fahrenheit. Okay, so what is the temp in Celsius and Kelvin for a room at 84 degrees Fahrenheit? Now, again, there's not really a nifty way to go from Fahrenheit to Kelvin. So go from Fahrenheit to Celsius first. And then once you've done that, you can do the shift to Kelvin. I'll give you guys 2.5 minutes for that one. Okay, so we're given that we have 84 degrees Fahrenheit. We want to find Celsius and Kelvin. So Celsius is going to equal our Fahrenheit minus 32 all over 1.8. In this case, it's 84. So 84 minus the 32 divided by the 1.8 gives us 28.888. Since I only gave you 2 to start with, we'll just round this to 29. So 29 degrees Celsius. For Kelvin, I'm just going to add 273. And we should get 29, 302 Kelvin. It's not like crazy complicated, right? I mean, and if this came up on a test, you'd be able to reference your notes for the equations. So it's nothing super scary, just be able to use them. I think the one thing I see is people will accidentally plug Celsius in here and they're trying to find Fahrenheit or vice versa. Make sure you're using the right equation, the inverse equation. Okay, let's add some more words. So we've got temperature, we've got heat. Now we've got this thing called heat capacity and another thing called specific heat capacity. So heat capacity is a property of a material, like every material out there has a certain heat capacity. And the heat capacity is the quantity of heat, usually it's given in joules, required to change the temperature of a certain amount of a material by 1 degree Celsius. So let's say I had 44 grams of gold and I want to raise it 1 degree Celsius, that would relate it to its heat capacity. We don't use heat capacity a whole lot in here. We tend to use specific heat capacity, which is even more refined. Specific heat capacity is the amount of energy, usually in joules, required to raise 1 gram of your material 1 degree Celsius. So let's say I had 1 gram of water and I wanted to raise it from 3 to 4 degrees Celsius. I would have to use the specific heat capacity of water in order to do that. And the specific heat capacity of water is actually 4.184. So here is a list of some of the common specific heat capacities. No, specific heat capacity, it's a funky unit. Okay, it's 3 units combined. It should look like that. It's joules over gram degree Celsius. So look at these everyday things. We've got metals, and then there's water. I mean, water's specific heat capacity is huge. It is way bigger than all the rest of them. You can see this in real life when you're boiling a pot of water. What gets hot first, the pot or the water? The pot gets hot way faster than the water does, right? After a minute or two, the pot will start getting warm. The water, it feels like, takes forever. The reason is because the water needs 4.184 joules of energy to raise every gram 1 degree Celsius, whereas let's say it's a copper pot, it only needs 0.385 joules to raise 1 gram of it 1 degree Celsius. So it's actually easier to heat these up than it is to heat up water. And then I'll always get students say, but water boil, you can turn water into a gas at a lower temperature than you can a metal. Well, yes, they have different boiling points, but that's talking about something different. So as far as specific heat is concerned, this is another reason why along the coastline, temperature tends to be more mild. So in winter, it's a little warmer right by the coast than it is inland, and it's a little bit cooler in summer than it is slightly inland, because the water acts as an insulator, because it takes a lot of time to heat the water up in summer, and it takes a lot of time for that water to cool down in winter. And as the water cools down in winter, it releases heat, which makes the coastline a little bit warmer. So usually the coastline has a more temperate environment. So how do all these terms come together? Well, we have this big equation. It's not that big. It's not that dramatic. It's 4 or 5 variables. It's the Q equals MCAT equation. That's what I call it. So Q equals M times C times delta T. Q is sometimes written like lowercase or uppercase. Okay. Q is the amount of heat in joules. So think of Q as how much energy is being absorbed or how much energy is being released. All right. Versus our C value. I'm going to skip over M. The C value is the specific heat capacity. Sometimes you see this one, instead of being a C, they'll write it as an SH for specific heat. It means the same thing. So here's C. The specific heat capacity is in joules per gram degree Celsius. Okay, so because your specific heat is in this funky unit of joule, gram, and degree Celsius, all the other things need to honor that. So my Q or my heat has to be in joules because my specific heat is in joules. Okay, my mass, which is M, needs to be in grams because my specific heat is per gram value. And then my temperature, and specifically this is delta T. Does anyone know what delta means? That means change in. So the change in temperature, or T final minus T initial. Okay, T final minus T initial. This needs to be in Celsius because, again, our C value or our specific heat is per degree Celsius. So if you were given a specific heat and the other values like mass was in kilograms and temperature was in Fahrenheit, you need to change those to match up with whatever the unit of your specific heat is. Other things to note, final temperature minus initial temperature. So that means if your final temperature is bigger than your initial temperature, right? The thing went up in temperature, it got hotter. This will be a positive value. It means your Q is positive. It means that it's absorbed heat, right? It's gotten warmer. If your final temperature is lower than your initial temperature, so the thing got colder, that means it's released heat. That means this value will be negative and your Q value will be negative. That's okay. You can have a negative Q value. The negative Q value just means that the energy is being released into the environment as opposed to absorbed. That makes sense? Positive Q value means it's eating up that energy. It's increasing its temperature. A negative value means that it's releasing that heat. You want to, isolating variables again is something that gives you trouble. You can make a triangle for this. Divide it up, put the Q on top, put the M here, C, and delta T. Remember, this is a divider bar, and these are multiplier bars. Okay, so if we want to isolate for something, like let's say we want to solve for Q. Q equals mass times C times delta T, right? MC delta T. What if we want to solve for change in temperature? Okay, change in temperature for delta T is going to equal your Q value divided by your mass times your C value. You guys seen how to read that? This is a faster way to isolate variables if you're not good at isolating from here. If you know how to isolate from the original equation, then you don't have to worry about it. So let's work through a problem together on this, and then I'll give you guys a few to mess around with. So we'll do this one together. So there's a material called gallium, and it is solid at 25 degrees Celsius, and it melts at 29.9 degrees Celsius. All right, so it's right about your body temperature that this stuff will start to melt. So if you hold it in your hand, you can actually melt it just by the heat of your hand that your body's giving off. So this problem is asking how much heat must 2.5 grams of this gallium absorb from your hand to raise its temperature from 25 degrees Celsius to 29.9 degrees Celsius. And it says the specific heat capacity of gallium is 0.372 joules per gram degree Celsius. So if you were to see a problem like this on a test, you're going to want to pull out Q equals MCAT. It's talking about heat. It's talking about changes in temperatures. It's talking about specific heat capacity. That's not been referenced in any other way throughout this section. So I would just like right off the bat say, hey, I know I need to use Q equals M times C times delta T. Now we've got to kind of narrow down what do we have, what is our given information, and what are we trying to find here. So the problem says how much heat, and this throws people off a little bit. What do they mean by heat? Which variable is talking about heat? Probably you're narrowing it down to this or this, right? This is heat. This is specific heat, okay? This is the funky unit. This is the unit for just joules. So we want to solve for Q. So if we're going to solve for Q, that means we better have information on all the rest of the stuff. Do we know the mass? We do, 2.5 grams. Do we know the specific heat? We do. They give it to us at the very end here. Okay, they kind of throw it in as an appendix. So we have 0.372 joules per gram degree Celsius. And then do we have a change in temperature? Almost. We need to calculate it out, but we are going to end at 29.9. We're going to start at 25. So I'm going to take my 29.9 and subtract 25.0 to get, I put a parenthesis in there. What is that? 4.9 degrees Celsius. So I think the hardest thing for people with these problems is just getting from this to this. Once you've got this, then it's just plug and chug, right? Now, all we need to do is just stick the things in where they belong, like where their home is. So the mass is 2.5 grams. Even before you plug it into, just check and make sure the units are all happy. So gram and gram, Celsius and Celsius. So we're going to take that 2.5, we're going to multiply it by the 0.372 joule per gram degree Celsius. And again, I include all my units because I want to make sure they cross out, and we're going to multiply this by 4.9 degrees Celsius. So what happens to our gram value? It goes away, cancels. What happens to our Celsius? It cancels. What are we left with? We'll be left with just the unit of joule, which is good because we're trying to find heat. So we want to know a joule value, 2.5 times the 0.372 times 4.9. And we get a Q value. Q is equal to 4.557. We have two significant figures, so I'm going to round this to 4.6, and the unit on it is a joule. 4.6 joules of energy to raise this little sample of 2.5 grams of gallium from 25 degrees to 29.9 degrees. So your hand donated 4.6 joules of energy. Any questions on this setup? On like where those numbers were coming from, where they were going from? You can throw it in the chat. Otherwise, we'll do an example problem. Okay, let's do somebody in the chat. Is it 2 sig figs because of the change in temperature? Yes. And also the gram value is 2 sig figs as well. So the gram value 2.5 would narrow it down to 2 significant figures as well. But yeah, the temperature change dropped to 4.9, which is now 2 significant figures. These had 3 sig figs, but we go with the lowest decimal, not significant figures when we subtract, add and subtract. So that drops to 2 sig figs. So we honor 2 sig figs. Let's do an example from this worksheet that I've got here. You can find this on your Moodle page. I want you to solve number 3. Let me zoom this up a little bit for you. Okay. So number 3 says calculate the specific heat capacity of a piece of wood if 1,500 grams of the wood absorbs 67,500 joules of heat and its temperature changes from 32 degrees Celsius to 57 degrees Celsius. Okay, so you're looking for specific heat in this problem. So a little bit different from the last one in that you're solving for a different variable, but it's the same equation. So I'll give you all like 3-4 minutes to work through that. Let's come back together. Take a look at this one. So in this problem, it wants us to calculate the specific heat capacity. Where do specific heat capacities come from? Usually we get them experimentally, and then they live in like an appendix at the back of the book. So there is one specific heat capacity that I do want you to be pretty comfortable with, and that's the specific heat capacity for water. So if water has a specific heat capacity of 4.184 joules per gram degree Celsius, it's also the same number as your calorie to joule conversion, that 4.18. So you see that number a couple times. But in this case, we're dealing with a piece of wood that is like not a consistent material, right? It's not like a hunk of gold that like gold is gold is gold. Wood, like what kind of wood is it? Does it have more carbon in it? Does it have more nitrogen in it? So we're trying to discover what the specific heat is of this sort of undefined material, but we have all the other stuff. So we want to, well, let's put our given here. We're trying to find C. Hopefully you got to that point. You know you want to solve C. You don't even know what the problem is asking you to do. It is hard to work through the problem. So make sure you get your given and your finds. Some of our given information, we know the mass, right? That's 1,500 grams. We know the Q value. Q is heat. Q equals heat, which equals 67,500 joules. Okay. So many times I see people put this value for the C and vice versa. So just make sure when you're talking about heat, Q. When you're talking about specific heat capacity, C. Yes, they both have the word heat in them, but they are not the same thing. Delta T, 57 minus 32, which will give us 25, yeah, 25 degrees Celsius. The units that we have are gram, joule, and Celsius. Those are good. We like those. We need to get C isolated. So Q equals M times C times delta T. If I want to get this by itself, I need to move those guys to the other side. So C should equal Q divided by your mass times your change in temperature. Now we just plug it in. So what's our Q value? It's that 67,500 joules. Our mass we've got up here is the 1,500 grams. And then our change in temperature is that 25 degrees Celsius. Now this may feel like, oh, this is so much work to like lay it all out like this. But it makes solving the problem so much easier when you know what each thing is, and then you can just plug and chug. As you get better at these problems, you can probably just look at it and say, oh, I know that's the mass. I know that's the joules. I know that's the change in temperature. I'm just going to plug it in my calculator. But in these, for these, first ones that you're working through, really kind of be anal about it, so that you can see how the problem works. So we've got 67,500. We're going to divide it by that 1,500, and we're also going to divide it by the 25. And we end up with a value of 1.8. What are the units on this? Does any of these things cancel with each other? No, they all stay. And that's what we want, because remember, C is the funky unit. So it's joule per gram degree Celsius. So this mystery wood takes 1.8 joules to raise 1 gram of it, 1 degree Celsius. How y'all feel about that? Good? Not too crazy? Okay, it's just an equation. You just plug it in. I'm going to give you one more that I want you to do. Let's see. Okay. How much energy is released if you cool 18.5 kilograms of water from 87.8 degrees Celsius to 13.5 degrees Celsius. Okay, how much energy is released if you cool 18.5 kilograms of water from 87.8 degrees Celsius to 13.5 degrees Celsius? I will tell you there is one piece of information that isn't easily available, or it's not written on the board, but you should be able to find it in the slides. I'll give you guys 4 or 5 minutes to work on this one. All right, so this is a Q equals MCAT problem. Come on. Okay, let me change color. Okay. Oh. There we go. Q equals MC delta T. So given information, we know the mass. It is 18.5 kilograms. We know the change in temperature. It is T final minus T initial, which is 13.5 degrees C minus 87.8 degree C. So our temperature change will be negative. That is okay. That just means that our value will be negative, which means the energy is being released into the environment. So we get negative 74.3 degrees Celsius. We're trying to find energy released, which is Q. And what's Q? What is the specific heat? That's something that we don't have. But you should know the specific heat for water, or at least be able to reference it. So the specific heat for water, H2O, is 4.18 or 4.184 joules per gram degree Celsius. Any problem that involves liquid water will use that C value. So now we just plug it in, right? We take, well, hold on, pause. So let's check our units and make sure everything's good. This is in Celsius, this is in Celsius, this is in gram, this is in kilogram. Let's convert kilograms into grams before we put it into the equation. Remember, King Henry died before drinking chocolate milk. We're starting at a kilogram. We want to go to the base unit of a gram. So we move the decimal over 1, 2, 3 hops to the right, or 1, 2, 3. So we add 2 zeros. So 18,500 grams. Now we plug that into our equation. The mass, 18,500 grams times 4.184 joules per gram degree Celsius times the negative 74.3 degrees C. And we end up with a big number. Well, a big negative number. Negative 5,751,117.2. The units on this is joules. We want to round to 3 sig figs, right? 1, 2, 3, 1, 2, 3, 3 sig figs. So negative 5,750,000 joules. The negative infers that the energy is being released or given off. So it's still a lot of joules because it's like a good amount of water, right? I mean, 18.5 kilograms of water. It's a few pounds of water. It's a pretty big temperature change. You know, we're changing by 74 degrees Celsius. That's a lot. And the heat capacity of water is large. So we would expect that to be a big amount of energy. You wanted to write this in scientific notation, or it was asking 5.75 times 10 to the 6th joules. So any questions on specific heat capacity problems? You definitely can expect one of these, or at least one on your test. Your test is going to be, it's online and it's going to be multiple choice format. So this would be given to you as a multiple choice, which means, you know, it would have A, B, C, and all the numbers would be different. You would need to pick the one that's correct. Obviously, one of the answers would be the one with the kilogram plugged in instead of the gram. So you want to make sure you're looking at those details. Sometimes multiple choice is nice. Sometimes multiple choice will almost guide you in the wrong direction. So you want to solve like the answers aren't there. Do I need to put a negative sign before the scientific notation? Oh, yeah, we'd throw a negative sign there. Yeah, negative 5.75 times 10 to the 6. Sorry, joules. Anything else with this? Let's see, no's, no, shaking heads, no's. Okay. So that's the end of chapter 3. That is technically where we're supposed to stop, and we'll do chapter 4 next week, but I'm going to lecture on chapter 4 for a little bit, okay, because we haven't even gone for an hour. So let's lecture for, I don't know, maybe half hour or so, and then we'll call it a day, and then we'll be ahead for next week. Yeah. Okay. So this next chapter is all about atoms and elements. So we're going to kind of build like you build, your language. You start with letters and then you make words and then sentences. We're going to start with atoms and elements, and then we're going to make compounds in the next chapter. And then from there, we'll move into chemical reactions. So we'll put compounds together in a reaction. So here's our cheesy intro slide of like, let me get out of this. Experiencing atoms at the sea and in the mountains. So atoms are the foundation of all of our senses. All the things you can smell and taste, touch, hold, all are composed of atoms or are composed of molecules that are then broken down into atoms. So even like the decaying fish smell that you smell at a beach, those are made of amines, which are made up of atoms. Atoms are incredibly small, like so teeny tiny. Okay, if a single pebble from the shoreline contained, or a single pebble from a shoreline will contain more atoms than you or your children or your children's children could count if you counted for the rest of your lives. So the number of atoms in a single pebble far exceeds the number of pebbles in the bottom of San Francisco Bay. They have another relationship here. To get an idea of how small atoms are, if every atom within one small pebble were the size of the pebble itself, the pebble would be larger than Mount Everest. So lots of atoms, and they're tiny. Atoms compose matter. So remember, we talked about matter. We said it had to have mass and take up space. Well, when we talk about mass, it means it has to have some sort of atoms in it. So we'll have a variety of atoms in it. The property of the atoms determine the properties of the matter. So if you have a big hunk of gold, it's going to have the properties of the gold atoms, like the properties on the macroscopic scale are coming from the properties of the microscopic atom. An atom is classified as the smallest identifiable unit of an element. So if I had a hunk of carbon and I cut it in half and cut it in half and cut it in half all the way down, its most definable but smallest incremental unit would be a single atom of carbon. If I was to take the carbon atom and like slice that thing in half, it would no longer be carbon. It would be protons, neutrons, and electrons. An element is a substance that can't be broken down into simpler substances. So if you have, like a hunk of gold, I can't break that down into anything simpler through a chemical reaction. It's just going to be gold. If I cut it in half, it's still gold, right? Whereas water, I could, through a chemical reaction, break that down into hydrogen and oxygen. I could break it down into something simpler. This is up for debate, but they say there's roughly 91 elements in nature and another 91. So in turn, another 91 kinds of atoms. So however many elements there are, or however many types of atoms there are, scientists have succeeded in making about 20 synthetic elements. A lot of times, let's go forward to a periodic chart. So the elements usually up through like the early 90s are considered natural. We find them in nature. Bigger than that, the atoms get so big, their nuclei have so many protons and then really just so many neutrons in them that they're unstable and they want to decay really fast to something smaller. So a lot of these bigger elements, some of them aren't even, depending on the periodic chart you look at, they're not even named. These are all quote unquote synthetic, meaning that we created them in a lab under like really cold, really high pressure environments. But that idea of like what is synthetic and what is natural is sort of up for debate because, some of these heavier elements may actually exist in nature, just in very specific environments, like, the center of a black hole or some environment that's really, really dense. So the exact number of naturally occurring elements is controversial. Okay. So the story of the atom starts back like before Christ, BC. Democritus came up with a postulate about 400 years BC that said that, if you took matter and you divided it into smaller and smaller pieces, at some point you would reach a tiny indestructible particle. So think of it as like a tiny little ball and it's super hard, dense, and it's indivisible. So the atomos is what he called it, which is where we get the word atom from. And it's indivisible, meaning that you can't break it into anything simpler. He was the first person to come up with this idea. And it it was a long time. That was a long time ago, like over 2000 years ago that we had this idea. And then nobody did anything really with it until like 1808, which wasn't that long ago. That's younger than our country. So over 2000 years later, this gentleman, John Dalton, started to bring this idea back up and formulate a theory around it. The atomic theory. Why did it take so long? What happened in the early 1800s? Well, in the late 1700s, early 1800s, there was a big scientific revolution. Specifically, the scientific method was applied, which meant that people had to come up with a hypothesis. They had to prove it. They were thinking in a much more objective way, as opposed to before that, science was very anecdotal. So oh, I saw this, and so I think this happened, and I'm just only going to look for things that validate my point of view. Okay, the moon is made out of cheese, and I think it's made out of cheese because it looks like it's made out of Swiss cheese, and it looks like Swiss cheese, so that is in fact it. That was kind of how science was. Changed in the early late 1700s. So under the atomic theory by Dalton, he said each element is composed of tiny indestructible particles called atoms. That's kind of a ripoff of the 2000-year-old postulate, right? He added some other things, though. He said all atoms of a given element have the same mass and they have the same properties that distinguish them from other elements. So atoms that are carbon atoms, for instance, will have a specific weight. Doesn't matter if the carbon atom is sitting here at my desk or it's sitting on the other side of the universe. It will have the same mass and it'll have the same properties. And those properties are different than, say, a hydrogen atom that's sitting right next to it. Hydrogen will have its own mass and hydrogen will have its own properties, but that hydrogen will be consistent across time and space. And then the last thing, atoms combine in simple whole number ratios to form compounds. So anytime you have a compound, it'll always be whole number. Like water is H2O, hydronium is H3O, hydrogen peroxide is H2O2. We don't ever have H1.5, O6.2. Why? Why don't we have decimals? Because atoms are indestructible. Okay. Let's jump ahead 40, 50 years. And this physicist, J.J. Thomson, discovered the first subatomic particle. So we have atomic particles, which are atom size, and then we have subatomic, which are smaller than the atom. And so he started to break up the atom into something even smaller, which initially he discovered an electron. Okay, so the electron was found before protons or neutrons were found. He didn't know about the nucleus. He just knew that didn't matter what the material was, gold or copper or hydrogen, whatever. They all had these things called electrons, different numbers of them, and that these electrons had a very small mass and they had a negative charge, but they were uniform across all substances. Now, the atom as a whole has a neutral charge. So he came up with this idea of the plum pudding model, because I guess they ate a lot of plum pudding, which sounds disgusting, but we're going to go with it. So you've got a ball of pudding, And then the electrons are like little plums stuck in it. And the pudding is a positively charged sphere of pudding, and the electrons are negatively charged, and they balance each other out so that the whole thing is neutral. Is that how the setup of an atom is? No, that's definitely not the case. But he didn't know. This is the best he could come up with. It's not too bad, right? And the fact that he's able to find the electrons is pretty cool. So later on, this dude Rutherford ran this really famous experiment called the gold foil experiment, and he took a radioactive lead source that gave off alpha particles, and alpha particles are super high energy. And he shot those alpha particles at a very thin piece of gold. We're talking like just a couple atoms thick of gold foil. And then on the back end, he had this receptacle paper that would light up every time an alpha particle would hit it. So under Thomson's theory with the plum pudding model, these alpha particles should just go straight through, and they should hit the back end. Because when we're looking at this model, these alpha particles are so high energy and those electrons are so tiny, they won't interfere with each other. They're just going to go straight past. But that's not what happened. He found that some of the alpha particles went straight through. Some of them kind of got deflected, and some of them shot like back towards the lead source. He didn't know, why this was happening, but he knew that something on a subatomic scale was getting in the way of these alpha particles to deflect the alpha particles. And so what he ended up discovering was the nucleus, or he started to develop the nuclear theory of the atom. So the idea of moving away from the plum pudding model, where we have this gelatinous positive sphere, and instead saying, hey, no, there's this central nucleus inside the atom that is very, very dense. It contains two types of particles. It contains protons, which are positive, and neutrons, which are neutral. And then the electrons just sort of float around the outside of this, right? And the electrons have a negative charge. The protons have a positive charge. So the electrons like to hang around the nucleus because of that negative positive attraction. So a couple things that go along with the nuclear theory. Most of the atom's mass and all of its positive charge comes from the nucleus. So we usually don't take into account the electron's charge. We just sort of consider it like negligible, the electron's charge. But the protons and the neutrons both have a substantial amount of mass. All of that mass sitting right in this tiny little shell here in the center. Most of the volume of an atom is empty space. I mean, the size of this atom is from the outer edge here to the nucleus. The outer edge being the farthest extent that those electrons stretch out. Look at what's happening. Most of that is just a void, right? So what we thought was this solid, sturdy, continuous ball of matter is actually mostly empty space with a small amount of matter in the center. If you want to go down the rabbit hole, if you break up these particles into smaller particles like quarks, these are made up of mostly empty space with these little quarks. And depending on what theory you look at, if you've heard of string theory, the idea of string theory is that if you break up quarks, that they're made up of mostly empty space and a vibrating ring of energy. And depending on how that ring of energy is vibrating, you get a certain type of quark, which then gives you a certain type of subatomic particle like a proton or a neutron, and then gives you a type of atom. So at the base, all matter, everything we consider to be hard and solid, is just a symphony of vibrating energy. So there you go. Mind blown for the evening. But back to how we'll apply this to chemistry. So it's mostly empty space. The number of negatively charged electrons outside the nucleus is equal to the number of positively charged protons. When we're at a ground neutral, like if I had 5 protons, I would expect to have 5 electrons. The protons and electrons would balance each other out, so the charge would be neutral. The nucleus is super dense, makes up about 99.9% of the mass. The electrons are distributed in a much larger area. Matter is much less uniform than we thought it was. This is kind of interesting. If you took a single grain of sand, but it was only composed of nuclei. So instead of it being like the bouncy, voluminous electron space, we just took nuclei and stacked them next to each other. This single grain of sand that is just nuclei would weigh 5 million kilograms. So stripping out all the space and just packing the nuclei creates really, really dense matter. That's not something you guys encounter in everyday life, but they do believe that there are circumstances in like neutron stars or in black holes where they do strip away all that space in the atom and we get these really, really dense pieces of matter. As far as the proportionality of size of a proton to an electron, you can think of a proton as a baseball and an electron as a grain of rice. There's about a 2,000 time difference. So the electron, I mean, it has a little bit of mass. It's not that it doesn't have mass, but it's just so negligible in most of our calculations that we kind of ignore it. Electrical charge is a property of protons and electrons. So protons, positive, P and P. Electrons, negative. Neutrons, neutral, no charge. Note that two positive things will repel each other, two negative things will repel each other, and a positive thing and a negative thing will attract each other, right? Opposites attract. So that's why the electrons hang around the nucleus. Know that one positive charge, so like the charge from one proton and the charge from one electron will balance each other out to create something that's charge neutral. Electrons don't like each other, so they like to spread as far away from each other as they possibly can. That's why we get this sort of spherical shape, because they're getting away from each other in 360 degrees. I always get a simple question of, well, if two positive things don't like to be next to each other, why do protons sit next to each other in the nucleus? That is a very simple question with a very, very complicated answer, and I'm not going to go into it. Because I don't fully understand it, but I know it has a lot to do with like field theory and quarks and string theory. You have to get into like more advanced physics to figure out why two protons like to sit next to each other. For the sake of this class, you're just going to say, you know what, they're fine with each other. Okay. So here are the properties of protons, neutrons, and electrons. Proton and neutron have a similar mass, okay, but their charge is different. So protons have that positive charge, neutrons have a neutral charge. Electrons have a much smaller mass by like a 2,000th, but they have a lot of bang for their buck. So they're not very big, but they have a negative charge, and that negative charge is super important. Electrons in general are super important. They like are the reason things bond together. It's why we have things like H2O or methane or octane or whatever. Electrical storm provides evidence of charge and matter. Yeah, anytime you see a storm where you have lightning, there usually is a negative charge buildup in the clouds. And then there's a positive charge buildup on the ground. And the electricity that you're seeing in the lightning is a neutralization of that charge or a rebalancing of the charges. All right, so what makes an atom an atom? Like what makes a carbon atom, or in this case, what makes a helium atom, and an aluminum atom, an aluminum atom? The number of protons is the defining factor in your element, okay? So if you have 2 protons in your nucleus, you are helium, and you will have the properties of helium. If you have 13 protons, you are aluminum, and you have the properties of aluminum. That is known as the atomic number. Sometimes it's called the Z number. The number of electrons can change, okay? And it can still be the same thing. The number of neutrons can change and it can still be the same thing. The number of protons cannot change. If you change the number of protons, you change what the element is. If we look at this periodic chart here, a lot of times the periodic chart, the number at the top, it's like a whole number. That's the atomic number. That's how many protons you have. You do want to get your hands on a periodic chart. Your lab manual should have one in the back. So I would definitely have that for next lecture. So you can like write on it and draw on it and take some notes. Depending on the periodic chart you have, some periodic charts just have the symbol. Some periodic charts also have the name. I believe the one that you have in the back of your lab manual also has the name. So like this guy here is beryllium. Its symbol is Be. Its atomic number is 4, meaning it has 4 protons. And then it has this atomic mass, which is how heavy it is. That's the protons and the neutrons together. And if you're wondering why is that number decimaled, if protons and neutrons are all 1 values, we'll talk about that a little later. So looking at this periodic chart, what element has 35 protons? You don't have to write it in the chat. I'll just give you like 10 seconds. So 35 protons. The answer is bromine. Okay. So you read the periodic chart like you would a book. You start in the upper left-hand corner, you go across, and then go to the next row across, and so on and so on. So 1 is here, 2 is helium over here, 3, 4, 5, 6, 7, 8 through 10, so on and so on. When we get to bromine, bromine is number 35. 35 protons. If you have 35 protons, you're bromine. You can't be bromine with 36 protons, and you're krypton. You're no longer bromine. The names and the symbols, sometimes they correlate to each other, sometimes they don't. So like if we go back here, you know, hydrogen is H, okay, that works. Helium is He, okay, that works. We get to potassium. Potassium is not P, potassium is K. Phosphorus is P, okay, but potassium is K. Why is that the case? Well, because some of the names, symbols, or some of the symbols are based off of the Latin names. So the Latin name for potassium was kalium. That's where they got the K from. The Latin name for sodium is natrium. So sodium is Na, not S. Sulfur is S. Here's some other ones that are like sort of incongruent. So lead is Pb after plumbum. Mercury is Hg, iron Fe, silver Ag, tin Sn. Shouldn't be an issue for you guys as long as you are using a periodic chart that has the name and the symbol for it. Okay. Know though, if you end up going in person next year for like or next semester for 151, you do have to know the names because the periodic chart you're given just has the symbols on it. So you will have to know those trickier ones, but you guys are going to get so comfortable with the periodic chart anyway throughout the semester that you'll probably like learn them anyway. You won't even have to try and do it. Some of the elements were named after their properties. So argon is named after Argos, which means inactive. And argon is a noble gas, it doesn't really react with things. Others are named after countries, okay? Others are named after scientists. Some are named after, like bromine, for instance, is based off of bromos, which is Greek for stench, and it's really stinky. So all sorts of different names. Okay, so I think we're gonna stop there because we, let's see, slide 23, and that's my birthday number. Remember that, Candace? Yeah, we'll stop there because otherwise we won't have anything to do next week. If you have any general questions, throw them out. If you have personal questions, stay around and we can talk one-on-one. If you're having any issues submitting that first lab or figuring out what to do, stay around and we can talk about it. I can give you a little leniency on the first lab. Otherwise, enjoy your week and I will see you guys next Wednesday. Okay, you guys are great. Thank you. Bye. And if you don't have any questions, just log out so I know who does and doesn't need assistance. Okay, I got a couple of you here, so I'm gonna just throw some of you guys in the waiting room and call you in one at a time. Hey, Chrissy.
All right, there we go. I'm unmuted now.
How are you?
I'm good. How are you doing?
I'm doing all right. What's up?
So I submitted the lab one. Was that okay? Submitting it like with the pictures? Because I didn't know how else to get it.
Let me
like
check.
It had some of the answers on there, and then I've done some of them, but there was some like the temperature measurement that I couldn't figure out, or the volume measurement because I didn't have a 10 ml graduated cylinder like go by.
Okay, so I'm going to share my screen with you and I'm going to show you something for next week's lab that you're going to be like, okay. So do you see here on the Moodle page?
Yeah.
You see this section where it says all lab procedures and data here? Click
Yeah.
on that. That is going to give you the data so
Okay.
that you can't, because you can't run the experiment yourself, right?
Yeah, no, I don't have like the equipment. I mean, I got,
Right, so we
but-
give you the information and it's
Okay.
living here. Okay, so it'll be much easier to do the next
Oh.
lab, hopefully, because you'll have the information.
definitely.
So
Okay, that's
use
so much.
this,
Yeah.
so use this when you're doing the next lab.
Okay, and that's
Work
on
those
the
together.
Moodle.
Yes,
Okay, fantastic. That
yeah, you
helps.
find it at the very top where all the places where you submit the lab, it says all lab procedures and data here. So
Okay.
that's your go-to.
Awesome. Well, that's very helpful. Good deal.
Yeah.
All right.
Yeah.
Well, I submitted like what I could complete.
Okay, if you want to resubmit it, you can, and I can give you like I'll give you a little extra time. I don't have a problem for that. Okay. So if you do want to go back and flip through that and say, oh my gosh, there's the number, I know how to do this, that's fine. Okay.
Good deal.
And if not, then, we can just move forward with the next lab.
Awesome. So, and then the quiz, because I worked that night that we had to submit it, and I've been kind of working on it and trying to figure it out. And I should have done it earlier, but I'm doing in anatomy and physiology at the same time. I don't know why they cursed me like that, but I mean, it works pretty good because they kind of correlate with one another because we're doing chemistry in AMP right now. We're on the chemistry part. So it is kind of like a double class of learning the math of it, which I'm horrible with
Is the
math.
last name Lewis?
Yeah.
Okay, I'll give you an extension on that quiz until tomorrow evening at midnight.
I can work on that right now after we get done with this.
Okay, yeah, so the new due date is tomorrow at midnight.
Perfect. Perfect.
All right, but then moving forward, just make sure you get them done
You got
sooner
it.
than later. Okay?
Most definitely. I'm usually like on the ball with getting everything done.
It's tricky
Fine,
with these
but-
online classes. Everybody has it formatted a little differently. Everybody uses a different software, so,
Yeah, and I'm horrible with online work anyway. I tried that with a different college before transferring to AB Tech, and I'm like, I really want to go back to in person because I learn better in person. So,
Yeah.
especially with chemistry. I mean, that's something that really you got to get your hands in there, but you know,
Totally,
do the best
totally.
we
I
can
agree.
with what we can, with this COVID stuff going on.
Yes, you just got to do the best you can.
And now I